Hello and welcome to today's lesson where we shall be treating second derivative test for Extrema. In our last video, we had treated first derivative test for Extrema, where we used the first derivative to determine the nature of a critical point to be either maximum, minimum, or point of inflection. Given a function f of x and a critical value x0, we say that the critical point x0 f of x0 is 1, a relative or local maximum if the second derivative of the function at the critical point x0 is less than 0, that means it's negative. 2 would say that the critical point x0 f of x0 is a relative or local minimum if f prime prime, the second derivative at that critical point or critical value, is positive. And we say that the second derivative test has failed if the second derivative at that critical value is 0. And in this case, we can now use other tests to check what happens at the critical point x0 f of x0. We'll now take an example to illustrate the process. Example: use the second derivative test to determine the nature of the turning points of the function f of x equal x to the power 4 minus 4x cubed minus 8x squared plus 5. And here, turning points simply means what? Critical points as well. So, we are asked to check what nature are the critical points of the function, given here. But this time, we are asked to use the second derivative test. We proceed as follows. We first find the first derivative of the function f of x, which gives us what? 4x cubed minus 12x squared minus 16 x. And of course, we cannot find the critical point of any function unless we have known what the critical values are. So, to get the critical value or values of this function, we set the first derivative to 0 as usual. So, if we set f prime of x to 0, we get this: 4x cubed minus 12x squared minus 16x equal to 0, which can be factorized as 4x into x squared minus 3x minus 4 equal to 0. And if we solve this out, we get, for the first part, we get that 4x equal to 0, which implies that x is equal to 0. And for the second part, which is quadratic, we have that x squared minus 3x minus 4 is equal to 0, which implies that if we solve this equation, quadratic equation rather, we get that x is equal to 4 or x is equal to what? -1. So, for this function given to us, we have three critical values. The first is x equal to 0, the second is x equal to 4, and the third is x equal to -1, which implies that we shall equally have 3 turning points for the graph, or what you call 3 critical points for the graph. So, what are these critical points? We get them by substituting x equal to 0, x equal to 4, and x equal to -1 into the function f of x. So, f of 0, the first critical value, will give us 5. So that implies that the critical point at the critical value x equal to 0 is 0, 5. The critical point at the critical value x equal to 4 gives us -1, 2, 3. And this implies that the critical point at the critical value x equal to 4 is 4, -1, 2, 3. Lastly, the critical point at the point x equal to -1 is f of -1 equal to 2, implying that the critical point there is -1, 2. So, we now have 3 critical points corresponding to the 3 critical values we had obtained earlier. So, the turning points are 0, 5, the next one is 4, -1, 2, 3, and the third one rather is -1, 2. The next thing is, what are the nature of these critical points? Which of them is a relative maximum, a relative minimum, or probably a point of inflection? So, at this point, we now take the second derivative. From the first derivative here, we can take f prime prime of x, and that will give us 12x squared minus 24x minus 16. To investigate the nature of the critical point obtained here by second derivative test, which is this, what do? We just check what happens at the critical values x equal to 0, x equal to 4, and x equal to what? -1. So for the first one, f prime prime at x equal to 0 at the first critical value. Now, if you substitute f prime prime as, if you put x equal to 0 into this function, we get -16. And minus 16 is less than 0. We had said earlier that if the second derivative at a particular critical value is less than 0, then the critical point in question, x0, f of x0, must be what? A relative or a local what? Maximum. And here we have that f prime prime at x equal to 0 is -16, and -16 is less than 0. So by the second derivative test, it makes this turning point a relative what? Maximum. It makes it a relative or a local maximum. We now check what happens also at the second critical value. F prime prime at x equal to 4 gives us, if we substitute 4 into the second derivative function, we get 80. And 80 is greater than what? 0. Again, we had said earlier also that if the second derivative, okay, at a particular critical value is positive, it makes the critical point what? A relative minimum. And here we have that the second derivative at the critical point x equal to 4 is 80, and 80 is positive. So it makes the critical point to be what? A relative what? Minimum. A relative minimum. Or what we call a local minimum. We'll now check what happens at the third and final critical value. So f prime prime at x equal to -1 gives us 20, and 20 is positive. So once again, the third critical point is a relative what? Minimum. It's a relative minimum. So our critical point, we have 2 relative minima and 1 relative what? Maximum. As an exercise for you, I want you to use the second derivative test to determine the nature of the turning point of the function f of x equal to x over 1 plus x squared, and leave your answers in the comment section below. Thanks and bye-bye.